coordination compounds have a vast application in our day-to-day life, and isomerism is a very important phenomena in coordination compounds. To understand isomerism in coordination compounds, in last lecture we discussed stereo or space isomerism, specifically geometrical isomerism. In continuation, today we will discuss optical isomerism, optical isomers, optical activity, plane of symmetry method, the mirror image method, optical isomerism in complexes with coordination number 4 and optical isomerism in complexes with coordination number 6. Before proceeding further, let us recall what is isomerism and what are isomers. Isomers are two or more compounds that have the same chemical formula but a different arrangement of atoms. Because of the different arrangement of atoms, they differ in one or more physical or chemical properties. Two principal types of isomerisms are known among coordination compounds: structural isomerism and stereoisomerism, which is also known as spatial isomerism. These two isomerisms can be further subdivided. As you know that structural isomerism can be subdivided in linkage isomerism, coordination isomerism, ionization isomerism, solvate or hydrate isomerism and polymerization isomerism. And stereoisomerism can be subdivided in geometrical isomerism and optical isomerism. Let us discuss what is stereoisomerism and what are stereoisomers. Stereoisomers differ only in the spatial arrangement of atoms or groups about the central atom. It is possible only in the complexes having coordination number 4 or greater than 4. The two types of stereoisomerisms are geometrical isomerism and optical isomerism. Our main emphasis will be on optical isomerism today. Optical isomerism occurs when a molecule is not superimposable with its mirror image. It is so called because the two isomers are each optically active. That is, they rotate the plane of polarized light in opposite directions. Optical isomers interact with polarized light in different ways. Separate equimolar solutions of each rotate a plane of polarized light by equal amounts but in opposite directions. Optical isomers are called dextro and levo isomers. One solution is dextrorotatory and the other is levorotatory. The dextrorotatory solution rotates the light towards right and levorotatory solution rotates the light towards the left, and the phenomena by which a plane of polarized light is rotated is called optical activity. Alfred Werner was the first person to demonstrate optical activity in an inorganic compound, that is, the compounds not of biological origin. Louis Pasteur had demonstrated the phenomena of optical activity many years earlier in organic compounds of biological origin. Optical activity can be measured with a device called a polarimeter. Here you can see the polarimeter. The plane of polarization of plane polarized light is rotated through angle theta. Here you can see the angle of rotation. This is plane polarized light, which when passes through the compound is rotated through an angle theta. A single solution containing equal amounts of two isomers is called a racemic mixture. This solution does not rotate a plane of polarized light. The equal and opposite effects of the two isomers exactly cancel. To exhibit optical activity, the dextro and levo isomers must be separated from each other. This is done by one of a number of chemical or physical processes broadly called optical resolution. Optical activity refers to whether or not a coordinate compound has optical isomers. A coordinate compound that is optically active has optical isomers, and a coordinate compound that is not optically active does not have optical isomers. With the knowledge of symmetry and mirror images, understanding optical isomers is not very difficult. There are two ways in which optical isomers can be determined: using mirror image method or using plane of symmetry method. Let's go through a quick review of symmetry and mirror images. A mirror image of an object is that object flipped or the way the object would look in front of a mirror. For example, the mirror image of your left hand would be your right hand. Symmetry refers to when an object looks exactly the same when sliced in a certain direction with a plane. The plane of symmetry method uses symmetry, as its name indicates, to identify optical isomers. In this method, one tries to see if such a plane exists, which when passes through the coordinate compound produces two exact images. In other words, one looks for the existence of plane of symmetry within the coordinate compound. If a plane of symmetry exists, then no optical isomers exists. On the other hand, if there is no plane of symmetry, the coordinate compound has optical isomers. Furthermore, if a plane of symmetry exists around the central atom, then that molecule is called achiral. But if a plane of symmetry does not exist around the central molecule, then the molecule has chiral center. The mirror images method uses a mirror image of the molecule to determine whether optical isomers exist or not. If the mirror image can be rotated in such a way that it looks identical to the original molecule, then the molecule is said to be superimposable and has no optical isomers. On the other hand, if the mirror image cannot be rotated in any way such that it looks identical to the original molecule, then the molecule is said to be non-superimposable and the molecule has optical isomers. Non-superimposable means the structure cannot be rotated in a way that one can be put on top of the other. This means that no matter how the structure is rotated, it cannot be put on the top of another with all points matching. An example of this is our hands. Both left and right hands are identical, but they cannot be put on top of each other with all points matching. An object that is not superimposable with its mirror image is said to be chiral. Remember that if the mirror image is superimposable, then no optical isomers exist, but if mirror image is non-superimposable, then optical isomers exist. Isomer which rotates the plane polarized light to the right is called dextrorotatory or D form, and the isomer which rotates the plane of polarized light to the left is called levorotatory or L form. Complex with the coordination number 4 and 6 show this type of isomerism. Let us discuss the optical isomerism in complexes with coordination number 4. When a metal ion has coordination number 4, complexes can have two types of geometries, tetrahedral and square planar. Square planar complexes cannot have optical isomers because all planar compounds have plane of symmetry. Now let us have an example of a tetrahedral compound C H Br Cl F. This is carbon, its hydrogen, fluorine, bromine and chlorine. Is this molecule optically active? In other words, does this molecule have optical isomers? Let's take the mirror image method first. Note that this mirror image is not superimposable. In other words, this mirror image cannot be rotated in any such way that it looks identical to the original molecule. Remember, if the mirror image is not superimposable, then optical isomers exist. Thus, this molecule has optical isomers. Let's try approaching this problem using the symmetry method. If we take the original molecule and draw an axis or plane of symmetry, this is what we get. Since the left side is not identical to the right, this molecule does not have plane of symmetry and thus can be called chiral. Additionally, because it does not have a symmetrical center, we can conclude that this molecule has optical isomers. In general, when dealing with a tetrahedral molecule that has 4 different ligands, optical isomers will exist. No matter which method you use, the answer will end up being the same. So, this was the discussion about the optical activity or optical isomerism in 4 coordinated complexes. Now, we will discuss the optical activity or optical isomerism in 6 coordinated complexes. As you know that 6 coordinate complexes have a geometry octahedral. First, we are going to discuss the type of complexes M, A3, P3. Here, M is the metalline, A and B are 2 types of ligands. Let's analyze the octahedral compound FeCl3F3. Now, this is iron, these 3 are fluorines and these 3 are chlorine. If we try to attempt this problem using the mirror image method, we notice that the mirror image is essentially identical to the original molecule. In other words, the mirror image can be placed on top of the original molecule and is thus superimposable. Since the mirror image is superimposable, this molecule does not have any optical isomers. Let's attempt this problem using the symmetry method. If we draw an axis or plane of symmetry, this is what we get. Since the left side is identical to the right side, this molecule has a symmetrical center and is an achiral molecule. Thus, it has no optical isomers. Let us examine the compounds of the type M, A2, B2, C2, where M is the metalline and A, B and C are 3 monodentate ligands. An example of this type of compound is cis-diamine, cis-diaqua, cis-dibromido, chromium 3. Cis geometrical isomer exist in 2 forms that bear the same relationship to each other as left and right hands. They are non-superimposable mirror images of each other and are called optical isomers or enantiomers. Complexes 1 and 2 are mirror images of each other. To see that they are not identical, imagine rotating second image about its vertical axis by 180 degree so that the 2 bromide ligands are at the left as they are in image 1. Then second has the H2O ligand at the right front position and NH3 ligand at the right rear position, which is not the same as in first image. No rotation of second image makes it identical to first image. Thus, these 2 arrangements are non-superimposable mirror images of each other. Stereo images of these 2 complexes appear in this figure. Here also you can see that these two images are non-superimposable to each other. Therefore, it can be said that cis-diamine, cis-diaqua, cis-dibromido chromium 3 ion has optical active isomers. Now, we are taking another example of Ma2P2C2 type of complexes. The example taken here is Pt Py whole twice, NH3 whole twice, Cl2 2 plus. Here you can see that cis isomer of this are optically active as the mirror images are non-superimposable. Therefore, this complex, or we can say that cis form of this complex has optical isomerism and contain D and L forms. Let us take the compounds of the type M, A, B, C, D, E, F, where M is the metal ion and A, B, C, D, E and F are 6 different type of ligands. An example of this type of complex is Pt, Py, NH3, NO2, Cl, Br, I. You can see the mirror image of this complex is non-superimposable. Therefore, this type of complexes has optical isomerism and exist in D and L forms. The different kind of hexa-coordinated complexes containing at least one chelating ligand show optical activity. You might be knowing what are chelating ligands. Chelating ligands are those ligands which have more than one donating centers and form rings with the metal ions. Let us discuss some examples of the complexes containing at least one chelating ligand. First, we are discussing the complexes of the type M, AA2 XY or M, AA2 X2. Here AA is a bidentate symmetrical ligand of the type ethylene diamine, that is NH2, CH2, CH2, NH2, and X and Y are simple monodentate ligands. In this example, trans isomer is optically inactive while cis isomer is optically active. Here is trans isomer. You can see here is axis of symmetry, therefore, this isomer, that is trans form, is optically inactive. But in cis form, there is no axis or plane of symmetry and also the mirror image is non-superimposable. Therefore, cis form of the complexes of the type AA2 XY or AA2 X2 are optically active. Let us take another example of the complexes of this type. Example is PtCl2 En whole twice. Here En is symmetrical bidentate ligand ethylene diamine and Cl is monodentate ligand. You can see the mirror image of cis isomer is non-superimposable and also there is no element of symmetry. Therefore, cis isomer of this complex is optically active, but trans isomer of this complex will be optically inactive. Here is the stereo view of the cis isomer of the complex COCl2 En whole twice. Here also you can see cis isomer is optically active as there are no element of symmetry and the mirror images are also non-superimposable. Now we will be discussing the complexes of the type MAA3. Here AA is again a symmetrical bidentate ligand. Octahedral complexes with 3 bidentate ligand show the optical activity. Here you can see this type of octahedral complex in which 3 symmetrical bidentate ligands are attached. The complex is tris ethylene diamine cobalt 3 ion. Here is the original molecule and this is mirror image. If you rotate the mirror image of this complex by 180 degree, you will get this type of figure. This is not superimposable on the original image. Hence, this type of complexes are always optically active. Here you can see, here is the stereo view of two optical isomers of tris ethylene diamine cobalt 3 ion. You can see the stereo view of another example of this type of complexes FeOX3 3 minus. Here OX is the ligand oxalato, which is a symmetrical bidentate ligand. These two are also optically active. Here is the mesoform of tris ethylene diamine cobalt 3 ion. Mesoforms are always optically inactive because of internal compensation. So, this was all about optical isomerism in octahedral complexes. You must remember 2 points to see optical activity in complexes. First, the mirror image of the compound must be non-superimposable, and the second, there must be no element of symmetry in the compound. In the end, let us revise what we have discussed today. Today we talked about optical isomerism, optical isomers, optical activity, plane of symmetry method, the mirror images method, optical isomerism in complexes with coordination number 4 and optical isomerism in complexes with coordination number 6. In next lecture, we will continue with valence bond theory.